Hey everyone, welcome to The Explainer. Today, we're going to act as your personal math tutor and totally master the hidden geometry of intersecting lines. I'm absolutely thrilled to guide you through this interactive masterclass. We're taking those tricky concepts that always seem to trip students up on exams, and we're going to make them completely second nature to you. So, grab your digital notebooks, settle in, and let's get ready to decode some geometry.
Okay, let's dive right in. Just take a look at this massive, complex web of lines and angles. It probably looks pretty intimidating at first glance, right? I mean, you've got rays shooting out everywhere from point M, little stars indicating equal angles, missing values. It's like an absolute maze. And honestly, it's completely normal if your brain's first reaction is just to freeze up a little bit.
But have you ever wondered how to easily decode the hidden rules behind all those intersecting lines? Well, I have some great news for you. By the end of this quick session, you're going to possess the mathematical superpowers to solve exactly this kind of intense puzzle with zero panic. Seriously, we're going to learn the two master rules that unlock every single problem of this type.
So, let's start with our first golden rule, vertically opposite angles. What this essentially means is that when two straight lines cross and form an X, the angles directly across from each other, they're identical twins. Technically, they're two non-adjacent angles formed by the intersection of two straight lines. But the absolute most important word to remember here is congruent. They are always equal in measure. If the top angle is 50 degrees, the bottom angle is exactly 50 degrees. It really is that simple.
Let's actually see this in action with a worked example from your worksheet. We've got two intersecting lines forming that classic X shape. We're given that the measure of angle AMC is 129 degrees, and the measure of angle DMB, which is directly opposite to it, is represented algebraically as 2x minus 7 degrees. Watch closely as we write out example 1 step by step. Because they're vertically opposite, step 1 is to just set them equal. 2x minus 7 equals 129. Why do we do this? Because setting up that equation is literally the anchor for the whole problem. Notice how we have to carefully balance the equation by moving the negative 7 across the equal sign so it becomes a positive 7. That's step 2. Then for step 3, we combine the numbers to get 2x equals 136. Finally, to get x all by itself and finish our puzzle, we just divide both sides by 2.
And this brilliantly illustrates just how satisfying it is when the algebra finally clicks, giving us our final answer of 68 degrees for x. By writing out every single step gradually like this, we completely eliminate the chance of making a silly addition or subtraction error.
Okay, let's move on to our second concept and see how this builds. When multiple lines meet at one single dot, completing a full circle, they must always add up to exactly 360 degrees. These are known as accumulative angles at a point. Just imagine standing in the center of a room and spinning all the way around until you're facing the exact same direction again. You just turned 360 degrees. The exact same logic applies to these geometry problems. Every slice of the pie has to add up to the whole 360.
Now, before we solve a problem using this new rule, we really need to talk about a massive trap. Always remember that little square symbol means exactly 90 degrees. You've got to be careful here because so many students make a mistake in this step on exams. They just forget to include the 90-degree value in their equation simply because it's drawn as a symbol instead of a number. If you miss that little box, your entire 360-degree equation is going to be wrong.
Let's apply this right now to example 2. Here we have several rays meeting at a common point M, and they form 4 distinct angles: 110 degrees, our sneaky 90-degree right angle, 5x degrees, and 2x minus 1 degrees. Step 1 is to take all 4 of those pieces and add them together to equal 360. The crucial point here is to carefully write out your big, long equation first. You want to combine your like terms, so the 2x and 5x becomes 7x. Then your numbers, -1 plus 90 plus 110 becomes 199. Doing this keeps our equation clean and organized before we even try isolating the variable. So that gives us 7x plus 199 equals 360. Next, we subtract 199 from 360 to get 7x equals 161. And finally, we divide by 7.
And after dividing 161 by 7, our final calculation reveals that x equals 23. Look at how beautiful and organized that step-by-step algebraic process is. When you really break it down, a super complex geometry diagram just turns into a simple, manageable equation.
All right, now here is a very common exam question designed specifically to test if you can spot vertically opposite angles when they're hiding inside some algebra. This one is straight from the classwork section of your worksheet. We see an X shape formed by intersecting lines. Over on the left, we have 45 degrees, and directly across from it on the right, we have 3x plus 15. Now there's also a 2y plus 50 on top, but let's ignore that for a second because we're just focusing on finding x right now. So here's what I want you to do. Grab your digital notebook, pause the explainer right here, and try to apply that first rule we learned to solve for x completely on your own. Seriously, try it out. Treat this like a real classroom. Write down your steps and see if you can isolate x before I reveal the answer.
All right, let's see how you did. Let's see a quick trick. Simply set 3x plus 15 equal to 45, because remember, they're vertically opposite. Then smoothly move that positive 15 over to the other side of the equal sign to make it a negative 15. That gives us 3x equals 45 minus 15. We simplify that to get 3x equals 30. And finally, just divide both sides by 3. If you calculated that x equals 10, give yourself a massive pat on the back because you totally nailed it. You accurately identified the geometric relationship, translated it perfectly into algebra, and solved it flawlessly.
Okay, let's level up with one more diagram from your classwork. This one features angles around a central point M, and it includes an 85-degree angle, a 25-degree angle, and yep, there's our sneaky little right angle box. We also have ray MD and ray MY in the mix. This is a classic accumulative angles problem, and the real secret to solving it is just careful observation.
I want you to pause again for just a second. Visualize how you would write out the sum of all these angles, setting them equal to 360 degrees. You don't even have to solve the whole thing right now. Just mentally practice building that long equation. And be honest, did you remember to substitute the number 90 in for the black square? If you did, you are completely on the right track.
Before we wrap things up, let's quickly lock in our key takeaways from today's session. Number 1, opposite angles are equal when straight lines cross. Number 2, angles forming a full circle around a point always add to 360 degrees. Number 3, never ever ignore the 90-degree box. And number 4, always write out your algebra step by step. These rules are your tools. If you use them methodically, absolutely no angle problem can defeat you. Now we're bringing back that incredibly intimidating diagram from the very start of our lesson, but this time it is your final homework challenge. The problem states that the intersection of lines AB and CD forms point M. It gives us the measure of angle AMC as 135 degrees. If you look closely, you'll spot it. It's the wide angle right at the top. Your mission is to find the measure of angle AME. And hey, notice those 3 little star symbols? That implies those 3 smaller angles at the bottom are all perfectly equal to each other.
So, are you ready? Take everything you've learned today about vertically opposite and accumulative angles and see if you can solve this final puzzle. I challenge you to write out every single step, map out those opposite angles, and find that missing value. You absolutely have all the skills you need now. And as you solve this, I want you to ponder something. If these strict rules apply so perfectly to lines on a flat piece of paper, how do you think they change when we start drawing lines on a 3D sphere, like our planet Earth? Good luck and happy calculating!